Hello and welcome to the Building IQ 10 on the 10th Tech Podcast series, where a range of artificial intelligence, machine learning, and data science topics are explored in 10-minute episodes each 10th of the month. In this episode, we speak with Building IQ's senior data scientist, Dr. Rami Khushaba. Rami has computer and electronics engineering degrees and a PhD in biomedical engineering. He has worked in fields including sleep apnea breathing disorder detection using machine learning. Thanks for your time today, Rami.
Thanks for having me, Christine, and thanks everyone for listening.
Rami, I understand you came to data science for the building industry in a roundabout sort of way. Tell us your story about how you transitioned from the medical field looking at sleep apnea disorder to machine learning for buildings.
So being with like a giant medical device company here in Sydney, I've been looking at records of like human breathing for 5 years with data collected from all parts of the world. And by looking at the data, you can see like the pattern of breathing for the human being is really close to the pattern of energy consumption in commercial buildings. If you look at, like, for example, the abnormalities that could be there, like human beings snore, buildings also snore, which they call the oscillation. We tend to have sometimes some sort of breathing stopping, which is like known as apneas. The buildings also have apneas during night when the HVAC system is off. We could have an early spike and then flattening of the breathing, which is called breathing limitation. The buildings also have that sort of pattern, which is due to the like fixed set points. And like so many other different patterns, the similarity is huge. So by looking at what I was doing using machine learning on human breathings, I saw like a direct like potential for me to apply the same algorithms on the HVAC system signals, because eventually at the end of the day, to me, it was like I'm just changing the patient. Instead of human being, I'm looking at commercial buildings. These were my new patients.
You've been instrumental in the development of Building IQ's Epiphany inference engine. Maybe walk us through the parts of the Epiphany engine and help us understand how they all work together.
Sure. So the whole idea started by looking at like the way the buildings work. So everything is based on a set of rules, but in reality, problems can happen and the rules are no more like followed. And that's where we needed something like the Epiphany engine to guide us by using artificial intelligence to uncover how the data is interconnected, depending and influencing each other instead of just following a simple set of rules. So what Epiphany gives you overall is the ability to distinguish your own offering, like by focusing on the data and what the data is telling you, how things like assets and components are working with each other, rather than just relying on the rules. So the main parts of the Epiphany engine were the inference, influence heat map, the delta heat maps, and the correlation map. Each one of them has a specific like job to do. For example, the influence heat maps can allow you to monitor the change in a certain reference point. For example, the total building power. So you can look at the total building power and you say, okay, I have a double up like in energy consumption today. Why is that happening? Who's contributing to that? Which part of the building has caused this double up in the power? And this is exactly the kind of question that the influence heat maps allow you to do. On the other hand, the delta heat map says, okay, you told me what's happening today, but how's that different from yesterday? And that's where the delta heat maps come in and say, okay, here's the influence heat map for yesterday and today, and here's the difference between the two, which immediately flags the components that were not active or the assets that were not being used or utilized yesterday, and they are being heavily utilized today and are affecting the power consumption. And then the last part, which is the correlation map, it comes in and it says, okay, you told me that this specific component wasn't working yesterday and is working today and it's consuming a lot of power, but why? Who caused this component to kick in so heavily and consume so much energy? And that's the question that the correlation map answers, which is what is causing or what is driving this sort of behavior? Not only that there is a relationship between the components, but what is actually the main cause or the root cause that is pushing these components to operate in like the way they are doing today, which causes like extra energy consumption.
Let's focus on the influence map here specifically. Our listeners may be wondering what a use case might be and what is the benefit to building owners for these influence maps?
So let me start by giving you a simple example. So we have a NOC, like a network operation center, in some part of the world. And those guys, what they do is that they go through all the time series or the data coming from all the sensors, from the IoT sensors. And sometimes, like, you're talking about, like, small buildings could have a couple of hundreds, like 200, 300 of these coming every single day, like every single minute, even in some situations, depending on your sampling frequency. So think about someone sitting like there and looking at 200 time series, trying to figure out, okay, what is the fault? Like, are there any faults today? How can I find faults? Where do I start? How do I even, like, start looking at the whole problem together? And then you're talking about small buildings which could have 200 to 300 time series, but in like a decent size like building, you could have at least 8,000 time series or 8,000 sensors sending you data all the time. How on earth could you actually go through all of these 8,000 like points or time series and figure out what's not working as it's supposed to be using the rule-based like technology that was available before we introduced Epiphany? So that's one example where we jumped in, and when we took out the list of all the problems that the NOC operation center generated for us, and then we did that automatically. We started by looking at the impact of all the mapped points or all the sensors and time series coming from the buildings and their impact on energy as a starting point or total building energy. And we started like looking like using information theory to rank these points in terms of their influence on the power, total building power, and which one is consuming more or impacting the power more than the others, and then start ranking these. And then by like monitoring these on a longitudinal basis and taking the difference between consecutive days, we found a significantly high correlation between what our system was finding and between what the NOC like team was actually generating manually after like browsing hundreds of sensors like through like many weeks. And we found like that strong correlation, which actually encouraged us to dig further into this direction and use like more advanced tools to focus on how to properly estimate the influence based on the data rather than what the rules tells us.
I think for many of us, data science is a bit of a mysterious topic. Help us understand these data science tools you alluded to previously. How are they actually applied in something like the influence map?
So in terms of, let's start with information theory. In information theory, we talk about probabilities and histograms, and we generate like the relationship, like we estimate the relationship between the variables or the different time series that we look at by using some sort of joint histogram and the individual histogram and the probabilities. Like, what's the probability that this signal is taking this value and like sensor 1 and the sensor 2 reading is taking this value? So you build some sort of knowledge based on the data, and from that knowledge you start advancing the mathematical terms to look like for what is the overall relationship between these two variables telling me, and how does that like impact another curve. So the whole idea is that you look at something like Venn diagram. If you have ever seen these circles that overlap with each other, the more they overlap the Venn diagrams, the circles, the more they go into each other, it means the more there is a relationship between these two variables. And the more they move away from each other, which means less relationship or less influence. So I want to be clear about something over here is that having a relationship like between two variables does not necessarily tell you who influence who. Like, I can have two variables like x and y, and I can tell you there is a huge amount of information shared between x and y, where x could be a sensor and y could be the total building power. But is that really because x is impacting y or y is impacting x? Like in the first look, you don't have any idea unless you use different sort of measures. And these measures that we call the influence measures, these are the important measures that tell you the way or the direction of information flow. So where is information flowing from? Is it flowing from X to Y or Y to X, or is there another variable that you are not looking at, like variable Z? Z could be impacting X and Y, and so on. So it's all based on probabilities and histograms and joint distributions of two variables and kernel density, let's say, estimates, which is we're trying to estimate the underlying distribution of variables, how they relate to each other, and how another variable could actually change the distribution of like the original variable. And this is what we do in terms of the math. So information theory is one of the most like robust, like let's say, fields of study that has been used like significantly in this direction. And over here, you can look at like concepts like entropies, which is a measure of uncertainty about the upcoming values from the sensor, upcoming readings. You can look at mutual information, which is how much information are the two sensors or the two time series sharing with each other without necessarily telling you who's impacting who. You can look at other measures like transfer entropy and so many other measures that can all help you in your work.
Really interesting, Rami. Thank you so much. We appreciate you joining us on this episode of Building IQ's 10 on the 10th Tech Podcast. To listen to other episodes and learn more about Building IQ's technology-enabled services, visit buildingiq.com. Thanks for listening, and see you next month on the 10th.